Settle in and let the room stay dim, like a lamp turned low on purpose. You are standing in a quiet Victorian workshop where paint is mixed by hand, slowly as if hurry would spoil it. The air smells faintly of oil, dust, and old wood, and the only sound is the patient scrape of a spoon in a bowl. On the bench sits a small tin of powder that looks disappointingly ordinary in the light. But when the lamp finally goes out, it offers a soft afterglow, the kind that feels like polite magic and behaves like strict chemistry. Tonight, the Sleepless Scientist will walk you through the weirdly gentle science of glow paints, borrowed light, and where it goes when it fades. Nothing will rush you. Everything will simply change slowly in the dark. In this workshop, the first secret is almost insulting in its simplicity. Nothing in that tin is making light from nothing. It is just borrowing light, holding it briefly, then giving it back with bad manners and poor timing. In human language, you shine a lamp on a powder. In chemistry language, you kick electrons into a higher energy state, and they take their time coming back down. You watch the painter tap a little of the powder into oil paint and stir until it looks like pale flour. In the lamplight, it is beige and boring, like something meant for bread. That is the trick that fooled so many Victorian party guests. They expected enchantment to look like enchantment. Instead, it looked like housekeeping. The glow comes later, when the room stops helping. When the lamp goes out, the powder finally gets to speak. What you are seeing is light reappearing as the material relaxes. It is not infinite, and it is not free. It is a slow refund. Victorians had a word they loved for this general idea. Even when they did not separate it neatly, they called many things luminous. They used it the way you might say a person has a glow about them, meaning nothing precise. But in a workshop like this, precision sneaks in through the back door. Some powders flash bright only while the lamp is on. Other powders keep glowing after the lamp is gone. Those are different behaviors, and the difference matters if you want to impress someone in a dark hallway. If the glow stops the instant the light stops, that is fluorescence. It is quick, obedient, and a little boring once you understand it. The moment the energy source leaves, the glow collapses like a stage actor without applause. If the glow lingers, fading slowly, that is phosphorescence. It is the long, tired exhale of electrons stuck in awkward places. The Victorians did not always use those exact labels in casual life, but they noticed the timing with great care, because timing is what makes the dark feel haunted. The painter here is not thinking about electron traps. He is thinking about the effect on a mantelpiece clock. He is thinking about a sign in a theater corridor. He is thinking about a novelty that will sell because it looks like a small miracle. And safety labels are not yet part of the tradition. This is an era that puts arsenic in wallpaper and lead in paint and calls it fashionable. So the workshop treats the glow like a parlor trick first and a hazard never, a polite kind of magic made by people with stained fingers and no gloves. The lamp is lit again and the powder looks ordinary once more. That is another quiet lesson. Glow materials rarely look impressive under normal light. They look like chalk or sand, or the glamour is always reserved for when you cannot see properly. The Victorians adored that. They lived in rooms ruled by dimness. Candles, oil lamps, early gaslight, all of it weak enough to let shadows keep their jobs. So anything that seemed to produce light in the dark felt like a loophole in reality. Of course, it was not a loophole. It was just bookkeeping. Energy in, energy stored, energy out, and always with a fee. Because even a gentle glow pays its rent in heat. Not the kind of heat you feel on your skin, the quiet kind, bleeding away into the air, molecule by molecule. In the workshop, you can almost feel the patience of the process. The painter charges a sample, then covers it with a hand to keep it dark. When he lifts his hand, there it is again, soft greenish light, like a bruise on the air. Already, it is fading, and that fading is not a failure. It is the entire story. Phosphorescence is a slow leak from a container that was never meant to be watertight. Some electrons fall back quickly. Some get stuck behind tiny energy barriers, like a door that opens only if you jiggle it just right. So the glow comes out in drips, not a flood. This is why it feels alive. A living thing changes in time, even when you stare at it. A steady lamp does not. So in the Victorian mind, a fading glow feels personal. It feels like it is deciding to leave you. In reality, it is just taking the most probable path back to calm. The powder wants to be boring again. Everything in chemistry does. Even when the effect is pretty, the destination is always the same. Lower energy, more stability, less drama. You can watch the glow shrink in your perception, even as the material keeps emitting faint photons. Your eyes are already playing tricks. Your brain is already editing. It is the first time tonight you notice that the dark is not empty. It is full of adjustments. But stay with the paint for a little longer. In a Victorian workshop, the ingredients are often rocks pretending to be ingredients for dessert. Powders were milled, sifted, washed, heated, cooled. It was chemistry disguised as housekeeping. A classic early luminous material was calcium sulfide. That sounds clean, like something from a pharmacy shelf. In practice, it could be made by heating limestone or shells with sulfur. Limestone is calcium carbonate, which is just rock that once belonged to sea life. Add heat, change the structure, push the atoms into a new arrangement. Then you get a compound that can hold on to energy a little longer than it should. That is what you are buying when you buy glow. Not light, but delay. The Victorians also played with other sulfides. Zinc sulfide became important later because it glows nicely when treated the right way. But early makers were often working with whatever could be sourced and processed. Some powders were unreliable, and that unreliability became part of the charm. You charge it, it glows, and sometimes it does not. Congratulations, you have discovered impurities. In glow chemistry, impurities can ruin everything, or they can make the glow possible at all. A pure crystal can be too perfect, and perfection is bad for afterglow. You need flaws, small defects, places for electrons to get stuck, so a little contamination can create the traps that make phosphorescence last. That is an awkward moral for humans. Sometimes the magic is made of mistakes. In the workshop, the painter does not call them defects. He calls them batches. This batch is good. This batch is weak. This batch has a nicer green. And in the background, the real rules are humming away. When the powder absorbs light, it is not storing little chunks of brightness in jars. It is storing energy by shifting electrons into higher states. Then, slowly, those electrons return, releasing photons. The color of the glow depends on the energy gap involved. A larger gap tends to produce bluer light. A smaller gap tends to drift greener or even toward red. So, the glow color is basically a confession. It is the material telling you how far the electrons fell. Victorians did not talk about band gaps in casual conversation, but they did love categorizing colors. They would describe a glow as apple green, sea green, ghost blue. They would argue about which was more tasteful. That argument is just physics wearing a velvet coat. Now notice something else. In a dim workshop, a green glow seems brighter than a red glow, even if the emitted energy is similar. That is because your night vision is biased. Your eyes, in low light, lean hard toward sensitivity in the blue-green range. It is not romance, it is rods. Your retina has two main teams of cells. Cones handle color and detail in bright conditions. Rods handle sensitivity in low light, but they do not care much about color. And rods respond best to wavelengths that make greenish blue light. So, a green glow feels like it fills the room more than it really does. The glow is not just chemistry. It is chemistry plus a human sensor that evolved to see moonlit landscapes. This is why the same glow can look eerie or comforting, depending on what your brain expects. In a child's bedroom, it is a friendly star sticker. In a corridor at 1 in the morning, it is a suggestion that something is awake. But the powder is not awake. It is relaxing. It is the laziest kind of light. The painter sets down the bowl and wipes his fingers on a rag that has seen decades. The rag smells like linseed oil and old pigment, and maybe a little coal smoke from the street. You look again at the small tin of powder. It is so modest, and it is doing something that, if you describe it badly, sounds like fantasy. A rock that drinks light and spits it back later, but describe it correctly and it becomes almost sleepy. A lattice with trapped charges slowly finding their way home. There is a second category of Victorian glow, and it is where the mood shifts. The first kind needs charging. It needs a lamp, a bright day, some source of photons to absorb. The second kind does not ask permission. It glows without being charged because it carries its own internal unrest. That is where history stops being cute, but we are not there yet. For now, you stay with the borrowed light, the socially acceptable kind, because it teaches you a gentle rule about energy. Energy does not vanish. It changes form, it spreads out, it becomes harder to use. The glow fades because the stored energy is being released. Some of it becomes visible photons. Some becomes vibrations in the lattice, which is just heat in a quiet suit. So when the glow disappears, it has not gone to nowhere. It has gone to everywhere. It has been diluted into the room, into the bench, into the air, into you. Like warmth fading from a brick after sunset. The brick is not glowing, but it is still releasing stored energy. Slowly, relentlessly. And this is the part that people often misunderstand. They think glow-in-the-dark paint stores light the way a jar stores fireflies. No, It stores energy in a different form, then releases it as light again. It is closer to a spring that was compressed or a battery that was charged, except this battery leaks constantly and calls it a feature. That leak is what you see as afterglow. The painter might layer the luminous pigment over a pale undercoat because a bright base reflects stray photons back out, making the glow appear stronger. The glow is always fighting loss. Loss into the binder, loss into the wall, loss into heat. So you cheat. You choose white paint beneath, you choose a smooth surface, you choose thicker layers up to the point where the pigment clumps and ruins the finish. Chemistry is always a compromise between what works and what looks polite. In Victorian decorative arts, politeness often wins. They want the glow, but they want the surface to look respectable in daylight. So the luminous pigments are used sparingly. A tiny star on a ceiling, numbers on a clock face, a small detail on a novelty card. The effect is subtle, because subtlety is easier to sell as taste, and because some of these materials were expensive, or unreliable, or both. You watch a test strip being charged near the lamp. Then the painter walks it into the shadow under a shelf. The glow appears again like a shy animal. It is strongest at first, then falls off quickly, then lingers at the edge of perception. That curve is typical. A fast initial drop as the easy electrons fall back, then a long tail as the stubborn trapped ones take their time. If you could graph it, it would be steep, then gentle. But you are not graphing it. You are watching it with tired eyes, which makes everything feel slower. There is a quiet comfort in this fading, because it is predictable. The glow does not suddenly decide to flare. It does not plan surprises. It follows probability, and probability is very dull once you accept it. The Victorians did not have your modern language for electron states, but they had patience. They repeated demonstrations. They compared materials. They wrote notes that read like poetry because they lacked the right nouns. A scientist without vocabulary becomes a poet by necessity. They would say the stone has absorbed the sun. They would say it holds the day inside it. They were wrong in a literal sense, but close in a useful way. Light in, then light out. Now, if you let your attention drift just a little, you can notice the room around the glow. The workshop is quiet, but it is not silent. There is the faint crack of cooling metal somewhere. There is the soft, continuous breath of the building settling. And there is the small sound of your own body, which you cannot turn off. The glow makes the darkness feel populated, not by spirits, by information. Tiny photons carrying the news that electrons have moved, that a lattice has relaxed, that time has. And, in a Victorian setting, time is always part of the performance. This is an age obsessed with measurement. Thermometers, barometers, galvanic experiments, early photography. Invisible things becoming visible through instruments. Glow paint fits that obsession perfectly. It is invisible in the sense that the cause is hidden, but the effect is plain. As soon as the lamp goes out, it turns the dark into a laboratory. Without the laboratory's harshness, you can imagine the demonstrations. A guest is guided into a darkened room. A painted flower on the wall begins to appear. A clock face floats in the air. Numbers hovering without a candle. People laugh, then go quiet, because the quiet is part of the trick. And someone inevitably says, "How is it possible?" The answer is boring, which is why it is powerful. Because boring answers do not need your belief. They work even if you roll your eyes. They work even if you call them impolite. The painter, if pressed, might say the powder drinks in light. He might say it stores the day. He might even mention that certain stones do it better after being heated. Heat treatment can change crystal structure and create better traps. In modern terms, you are modifying defect sites, adjusting how charges get stuck. In workshop terms, you are cooking the rock until it behaves. Same reality, different accent. There is a particular Victorian fascination with the idea that materials can have memory. Not memory like a brain, memory like a habit. A tendency to respond the same way when treated the same way. Glow pigment has that habit. Charge it, it glows. Charge it again, it glows again. And if you keep doing it, you notice the habit has limits because the material gets tired in its own way. Not emotionally, of course. It is a rock powder, and rocks do not do feelings. But the crystal lattice can slowly change, and the binder can yellow, and water can creep in. So the same charging ritual gives you a slightly weaker glow over months and years. Congratulations, you have discovered that nothing stays new, not even novelty. In a practical workshop, you would call that poor quality. In a physics notebook, you would call it degradation, and you would sound less offended. Some of that loss is chemical. Oxygen and moisture can react with the surface, especially if the pigment grains are not protected well. Some of that loss is physical. Crystals get scratched, ground, and mixed, and their tiny defect sites change. And some of that loss is simply your perception learning the trick. The first time you see a wall bloom green in darkness, it feels like a secret. The 50th time, it feels like a clock doing its job. Your brain stops writing poems about it. It starts filing it under normal. That is the strange mercy of repetition. It turns the uncanny into furniture. Now, the lamp is still low. The powder still looks like flour, but the question that keeps scratching at the back of your skull is simple. When the glow fades, where does it go? You already know the polite answer. Energy spreads out, becomes heat, becomes harder to collect again. But you want the physical answer, the one with mechanisms and consequences. So you lean closer to the paint sample, as if staring can bully it into honesty. The afterglow is not a thing trapped inside waiting to be released. It is an event, repeated many times, in many tiny places. A single photon goes in, and later, a single photon comes out. Not the same photon, of course. That would be too neat. The absorbed light becomes energy in electrons and vibrations. Then, the system rearranges, and a new photon is emitted. This is why glow is never perfect. Some of the incoming energy leaves as heat, without any visible light at all. Those are the quiet losses, the ones you cannot see, but you always pay. If you could shrink down into the pigment grain, you would feel it as jitter, atoms shivering in place, passing little nudges along the lattice. That is what heat is in its dullest definition. Not fire, not flame, just vibration and impatience. And in a dim Victorian room, the heat is already everywhere. The candle warmed the air. The oil lamp warmed the glass chimney. Your body warmed the floorboards under your feet. So when the glow pigment wastes energy as heat, it does not stand out. It just joins the background choir. The visible afterglow is the part that survives that waste, the part that escapes as a photon your eyes can notice. And even then, your eyes are picky. You are not a neutral detector. You are a nervous system with opinions. In low light, you do not see the world as it is. You see the world as your rods can manage. And rods, those patient cells in your retina, have their own favorite colors. They are tuned toward bluish green, the kinds of wavelengths that moonlight leaves behind. So a pale green afterglow feels louder than it is. It feels like it fills the room, even if it only fills your perception. This is why glow paints often aim for green, not because green is mystical, because green is efficient in the language of human eyes. A faint red glow can be physically real and still look like nothing. Your rods will shrug and let it pass. Your cones would help, but cones demand brightness, and you do not have it. So color becomes a luxury, and sensitivity becomes your only friend. In the Victorian dark, this mattered. They lived with dimness as a constant companion. So they were experts, without realizing it, in how the eye adapts. If you sit in the dark long enough, your sensitivity climbs. It is not instant. It is a slow chemical reset inside your retina. The key player is a pigment called rhodopsin, sometimes called visual purple. It lives inside rod cells, and it is ruined by light on purpose. Light hits it, it changes shape, and that change triggers a nerve signal. Then your cell has to rebuild it, molecule by molecule, like repairing a tool. In bright light, you are constantly breaking rhodopsin. In darkness, you finally get time to rebuild your supply. So after several minutes, you begin seeing more with less light. Not because the room changed, because you did. This is where the workshop glow trick becomes a collaboration. The pigment releases photons slowly. Your rods become more sensitive slowly. Together, they create a feeling that the glow is holding steady. But it is not. It is fading, and you are compensating. You are meeting it halfway, like a polite guest walking toward a quiet host. There is also a tiny, humiliating detail about your pupils. You might imagine your pupils do the heavy lifting in the dark. They do help by widening to let in more light, but pupil size changes fast, in seconds. The real night vision change takes minutes, because chemistry is slow. Your eyes are not cameras with a simple aperture. They are living sensors with replenishing molecules. And because of that, the dark is not just the absence of light. It is an active state your body enters gradually. In the Victorian era, this changed how rooms were designed. Gaslight made interiors brighter than candles, but still uneven. Walls were painted to manage gloom and glare. Mirrors were placed to multiply weak light. Polished brass and pale fabrics were used like passive lamps. And when luminous paint entered the scene, it was another way to cheat. A tiny stored glow to guide a hand toward a door latch. A faint mark on a stair edge. A suggestion of safety. Of course, it was also used for silliness. A painted skeleton in a corridor, waiting to spook a guest. Victorians loved a controlled scare, the kind you could blame on science. But your eye turns controlled scares into personal ones. In low light, your visual system trades detail for sensitivity. Edges soften, colors collapse into gray, and your brain starts filling in gaps because it hates uncertainty. So a coat on a chair becomes a crouched figure. A curtain fold becomes a face. Congratulations, you are now a pattern recognition machine with anxiety firmware. This is not madness, it is efficiency. If you are an animal in twilight, missing a predator is worse than seeing one that is not there. So your brain is biased toward false positives. It would rather embarrass you than kill you. In a room lit by fading glow paint, you can feel that bias at work. The glow makes a few features visible and hides the rest. Your brain stitches a story from scraps. That story can be calm, if your life is calm, or it can be ominous if you are tired and alone. The chemistry does not care. The photons are emitted without emotion. It is your nervous system that writes the ghost stories. Still, it helps to know the rules because rules are soothing. And the rule here is that light does not disappear. It becomes less useful, less concentrated, more spread out. The glow fading is not a dying, it is a dilution. In strict terms, it is entropy increasing. Entropy sounds like doom, but it is mostly just fairness. Energy spreads out because there are more ways to be spread out. The universe prefers the option with more options. That is why your coffee cools. That is why your room equalizes in temperature. That is why glow pigments give up their borrowed energy slowly and then stop. They are not refusing to glow anymore. They have simply reached their lowest, laziest state again. And now your attention slides, as it always does at night, toward your own body. Because the strangest glow lab in the room is not on the bench. It is inside your head. Your retina is a chemical factory operating in silence. You have cells that detect single photons under the right conditions. Not all the time, but sometimes when your rods are fully dark adapted, one photon is enough. That is absurdly sensitive. It is also slightly inconvenient because your visual system is so sensitive that it can hallucinate light from its own noise. Random thermal events can trigger signals like false alarms. That is one reason deep darkness can feel grainy. Your eye is never perfectly quiet. It is living tissue, warm and restless. And warmth means motion, and motion means noise. So when you stare into a dim corner and you think you see flickers, sometimes you are seeing the chemistry of your own retina misfiring politely. It is not supernatural. It is biology running close to the edge of what is possible. This is why early experiments in vision were so strange. People would sit in dark rooms and report flashes and specks. Some thought it was the soul reacting to darkness. Others, more practical, blamed the eye itself. They were right. You can even press gently on your closed eyelid and see light that is not light. Those are phosphenes, pressure-induced signals. Your retina does not actually know what caused the electrical change. It just reports, like a tired clerk, that something happened. And your brain translates that report into what it knows best: brightness, patterns, little fireworks behind your eyes. So when you are listening to a story about glow paints, remember that you are also a glow device. Not in the sense that you emit light, at least not much, but in the sense that you convert energy into signals. and signals into experience. You are a translator of photons into meaning. And in low light, you become a translator who improvises. That improvisation shaped how people lived. A Victorian reader, hunched near a lamp, saw text with a smaller field of sharpness. They would move the page, adjust the angle, chase the best light. Their eyes worked harder, and their evenings were shorter. The idea of staying up late was different when darkness was expensive. So, a glowing paint on a clock face was not just decoration. It was a small rebellion against the cost of light. A way to check time without striking a match. A way to find the hour while half asleep without waking the room. It feels familiar because you still do it. You glance at a phone screen. They glanced at a faintly glowing number. Different technology, same human habit of wanting information without effort. And the glow, once again, was never endless. It faded as the night went on, so it trained a certain kind of patience. If you missed the bright phase, you accepted the dim phase. If you wanted it bright again, you had to charge it again. That is a gentle lesson, repeated in small ways. Convenience comes with conditions. Now, speaking of conditions, your mind drifts back to the powders themselves. Because the workshop is not just an aesthetic scene, it is a supply chain in miniature. Those luminous ingredients had to come from somewhere real. Some were made in-house, with heat and sulfur and luck. Others were purchased from merchants who sold powders the way they sold spices. A scoop of this, a pinch of that, a label in neat handwriting that promised wonders. And in the 19th century, mineral powders were an obsession, not only for glow, but for pigments, glass, ceramics, and medicines. The same crushed rocks that made paintings also ended up in faces, on walls, and in bodies. You are surrounded by a world of ground minerals pretending to be civilized. For glow effects, a big dividing line appears. Some materials fluoresce, some phosphoresce, and some do something else entirely, which will matter later. Fluorescence is the obedient one. Light in, light out. Immediately, like a polite echo, you shine ultraviolet light on certain minerals, and they bloom with color. Turn off the ultraviolet, and they stop instantly. There is no afterglow, because the electrons fall back quickly. In the Victorian era, ultraviolet itself was not a household word, but the effects could still be seen with sunlight or certain lamps and the right minerals. Fluorite is famous for this, and it gave fluorescence its name. It can glow blue under ultraviolet, like a cold flame. Some varieties show different colors depending on impurities. Once again, the magic is in the flaws. Calcite can fluoresce too, sometimes red or orange, sometimes blue. And certain organic dyes can fluoresce with startling brightness. Even quinine, the bitter compound in tonic water, fluoresces blue under ultraviolet. Victorians knew quinine well because it was used against malaria. They did not necessarily know its fluorescence, but they lived surrounded by compounds that could do it. So, the boundary between chemistry and spectacle was thin. But phosphorescence, the slow one, was the real prize for glow paints. Because it let you take light into darkness with you. It let you paint time onto a surface. And the minerals that did that were not always gentle. Even when the rock seemed harmless, the processing could be crude. Sulfides could smell, and sulfur can be unpleasantly honest. A workshop mixing these compounds could carry a faint stink of rotten eggs. Not always, but sometimes, depending on impurities and moisture. So your lovely glow came with the scent of swamps. That is the reality of chemistry. It rarely smells like romance. Still, the Victorians persisted, because humans love a controlled wonder. They love a substance that behaves differently in the dark. It makes the night feel less empty. It makes the world feel layered, like there are secret rules behind the visible ones. And there are. They just do not care about you. Now, if you let your imagination shrink again, down into the powder grain, you can picture a crystal structure like a hotel with bad management. Electrons are guests who should return to their rooms. But some doors stick, some hallways loop, some stairwells are blocked. So electrons wander, trapped in awkward places, waiting for a little extra energy to help them escape. That extra energy can come from thermal motion, from warmth in the room, which means temperature affects glow. A warmer environment can make trapped electrons escape faster, so the glow fades quicker in warmth. In colder conditions, the traps hold longer and the afterglow can persist. This is why some phosphorescent materials behave differently. In winter, your glow is not just light dependent, it is temperature dependent, because heat is a quiet key. The Victorians noticed this in their own language. They might say, "The powder is more lively on cool nights," or that it tires quickly near a fire. They were observing thermal activation without the vocabulary. And if you remember that your body is warm, you see another detail. A glowing object held in your hand may fade faster, not because you are stealing its light, but because you are warming it. Your palm is a little heater, and the pigment responds. That is intimate in a strange way. Your body temperature reaching into the lattice and changing how long it can hold energy. So even the simplest glow trick is a conversation between object and environment. Light in, heat out, time passing, eyes adapting. It is a whole system pretending to be a novelty. And now you can feel the outline pulling you toward the next thought, because you have followed borrowed light to its soft end. You have watched it fade, and you have accounted for where it went. It did not vanish. It dispersed into heat and faint photons and the noise of perception. And once you have watched a glow fade to nothing, it is hard not to ask a more unsettling question. What if it did not need charging at all? What if the glow came from inside, continuously, without ever being paid for by lamplight? That is when the parlor trick becomes a quiet horror. But before that, before you step into the chapter that harms politely over time, you need to meet the powders as they were in their mineral reality, because not every luminous ingredient was exotic. Many were simply rocks, treated with reverence and a mortar. In the trade, you would hear names that sound like fairy tale ingredients. Bologna stone, Canton's phosphorus. Names that imply mysticism, but mostly mean someone found a rock that did a thing. The Bologna stone story is one of the earlier famous ones, a kind of barite, barium sulfate, discovered near Bologna in Italy, that could glow after being heated strongly with charcoal, and it could become barium sulfide, which is phosphorescent. So the miracle depended on cooking a mineral until it changed identity. The workshop version of alchemy but with repeatable outcomes. This mattered culturally because it suggested that the world had hidden behaviors unlocked by process. Heat, grind, mix, and a stone becomes a light source. Temporarily, that idea made people bold. It made them curious, and it made them careless, because curiosity often forgets to wash its hands. When you grind minerals into powders, you make them easy to inhale. You make them easy to spread. A rock in a field is stable and quiet. A rock as dust becomes intimate. It enters lungs, it settles into fabric, it sticks to skin. Victorian workshops were full of dust, pigment dust, metal dust, coal dust, chalk dust, particles floating in lamplight like slow snow. So even the gentle minerals came with the general risk of breathing other people's experiments. A painter might develop a cough and blame the weather. The weather, politely, would accept the blame. Now imagine the specific minerals used for glows. Sulfides, yes, but also compounds containing heavier elements. Barium compounds, for example, can be toxic if soluble. Barium sulfate itself is very insoluble and used medically even today in imaging. But barium sulfide is different, and workshop chemistry does not always keep boundaries clean. So you had a mixture of substances, some safer, some less so, handled without modern caution. The glow was the product, the dust was the price. And the Victorians paid it slowly, because slow consequences are easy to ignore. They were also obsessed with cataloging. Minerals were collected in cabinets, labeled, admired, and sometimes licked, because people did that. A small taste to identify a specimen. They would say, "Congratulations, you have invented a hobby that doubles as poisoning." Still, from that messy curiosity came careful observation. You watch them learn slowly that the best glowstones are rarely the prettiest ones in daylight. You watch a dull gray lump outshine a sparkling crystal. Once it has been cooked and crushed, you think the glow must live on the surface, like dew. Wrong. The useful part is hidden in the structure, in the tiny mistakes inside the grain. A flawless crystal is like a perfectly sealed room. Nothing gets stuck inside it, and nothing lingers. A flawed crystal is full of crooked doorways. Electrons wander in, then hesitate, then take their time leaving. In practical terms, the workshop learns recipes. They learn that heating certain minerals with charcoal changes everything. Charcoal is not magic. It is a hungry sponge for oxygen. It helps pull oxygen away from compounds. It pushes reactions towards sulfides. So a sulfate can become a sulfide, and a non-glowing stone becomes a shy lantern. They did not say reduction reaction most of the time. They said it was awakened. And then they wrote down the temperature by describing the color of the fire. Because thermometers existed, but fire still spoke in colors first. A dull red heat, a bright orange, a white glare that makes you squint and look away. You stand close enough to feel that heat drying your eyelashes, and you realize the glow powder is born in violence, not in moonlight. It begins as a thing roasted and starved of oxygen until its chemistry changes. Then it is cooled, ground, and handled like flour, and it ends up on a clock face pretending to be gentle. This is how many inventions work. They are brutal at birth, then polite in the living room. Even the name phosphorus in old texts is slippery. In modern chemistry, phosphorus is an element, number 15, in the periodic table. In older writing, phosphorus could mean anything that glows. It meant light bearer, and it was used with a shrug. So you might read about a phosphorus made from urine, or shells, or minerals, and the writer may not mean the element at all. They may mean a substance that holds light or releases it, or simply looks eerie. That confusion is not stupidity. It is a language trying to catch up with reality. In a cabinet of curiosities, labels were often poetry, pretending to be taxonomy. But there is something steady beneath the romance. The glow always has a source. Sometimes the source is sunlight stored briefly, like warmth in brick. Sometimes the source is chemical energy released in a slow reaction. And sometimes the source is worse because it is not borrowed from the day. It is borrowed from the nucleus of an atom. And nuclei do not negotiate. You are still in the era of minerals and lamps, though, so you can take your time with the ordinary strangeness. Imagine a Victorian collector with a drawer full of labeled stones. He charges a sample on the windowsill during the day. At night, he brings it into a dark room and watches it breathe light. He notices it glows brighter after sunshine than after lamplight. That is a real observation. Sunlight includes more energetic colors, including ultraviolet, even if his eyes cannot see them. Some glow materials are charged best by those invisible wavelengths. So, the sun is a better key than his indoor lamp. He does not know the spectrum in detail, but he knows the sun works better and he trusts what works. This is how science grows. Most of the time, not as a grand theory first, but as a habit of noticing. Now your mind drifts from cabinets to workshops again, because the powders did not stay in private drawers. They ended up in paint. They ended up in varnish. They ended up in lacquered ornaments that tried to look expensive. And the binder matters, even if nobody wants to talk about it. A luminous pigment grain is like a tiny machine, but you have to embed it in something that sticks to a surface. Victorian binders were often drying oils like linseed or natural resins dissolved in alcohol like shellac, or glue-based mixtures for cheaper applications. Each binder changes the glow by suffocating it a little. If the binder absorbs too much of the emitted light, the glow looks weaker. If the binder yellows with age, the glow color shifts. If the binder holds moisture, the pigment surface can react and degrade. So, the paint is never just pigment. It is pigment living inside a chemical environment, a tiny habitat with rules. That is why recipes mattered so much, and why the same luminous powder could look different in two different workshops. One painter uses a clear varnish, another uses an oil that turns amber. One keeps the powder dry, another leaves it in a damp corner. One grinds it too fine and damages the crystal structure. Congratulations, you have turned your glow into a very expensive dust. The glow is fragile in a way the Victorians did not always respect, because the visible effect is tough enough to survive casual handling. It keeps glowing after being mixed, painted, dried, so it feels robust, but on the microscopic level, you are balancing defects and impurities and surfaces, tiny details that decide how long the afterglow lasts. Speaking of surfaces, The grain size matters too. A finer powder has more surface area, which means more places for moisture and oxygen to interfere. A coarser powder may glow longer, but look gritty in paint. So once again, you compromise. You choose the size that looks smooth enough in daylight and bright enough at night. Victorian taste demanded daytime respectability. Nighttime wonder was allowed, but only as a private indulgence. Now let the room go dark again in your imagination. The lamp wick lowers, the flame shrinks, and the air cools slightly. You watch a painted mark on a board. Wake up pale and green. It is never as bright as you want. It is always softer than memory. But softness is the point. In a sleeping house, a harsh light wakes the mind. A faint glow lets it drift. In the 19th century, faint glows also carried a certain status. It meant you had access to novelty. It meant you had a friend in trade or a taste for modern tricks. And it meant you trusted materials you did not fully understand, which is a very human trait. Now your attention slides toward a colder kind of glow. Not the charged kind, the borrowed kind. The kind that does not care whether you remembered to leave it under the lamp. The kind that shines anyway. Before you reach that, you should notice one more gentle category. Some things glow only while you rub them, or break them, or peel them. This is not phosphorescence. This is mechanical misbehavior turning into light. Triboluminescence is the formal name. It means light from rubbing or crushing. And yes, it sounds like a novelty candy. Certain crystals, when fractured, separate electric charges. That sudden separation can rip electrons through the air, creating a tiny spark. That spark can excite nitrogen molecules in the air, which then emit bluish light. So you get a flash, a brief cold wink. Victorians saw this with sugar crystals sometimes. They could crunch wintergreen candies in the dark and see faint sparks, a parlor trick that tastes like mint and electricity. It is the same general theme again. Energy in, energy out. With a conversion step in the middle, mechanical stress becomes electrical separation. Electrical discharge becomes excited gas. Excited gas becomes photons. And then it is gone. Because it was never meant to last. Now imagine a Victorian workshop hearing rumors of these effects. Stones that glow after sunlight. Crystals that flash when crushed. Liquids that glow under certain lamps. In that atmosphere, it was easy to believe the world was full of hidden light. And in a sense, it was. But hidden light does not mean friendly light. Some hidden light comes with invisible damage. That is the next chapter, and it is where the softness becomes uneasy. Because there is a kind of glow that is steady, a glow that does not fade in minutes, a glow that can last for years without charging. It looks like a gift. It is not. It is a leak from the deepest part of matter. You do not meet it properly until the late 19th and early 20th centuries, because you needed a new discovery first. You needed the realization that certain elements are unstable in a slow, patient way. They do not explode. They simply decay, quietly, relentlessly, and they shed particles and energy as they do it. The world learns this through strange accidents and careful work. Glass photographic plates fogging for no reason. Salts that seem to expose film even in darkness. a new kind of invisible emission, first called rays because naming is hard when you are surprised. In your mind, you leave the Victorian paint bench for a moment. You step into a later laboratory, one with sharper smells, acids, warm metal, old paper. There is a tray of crystals that look innocent. They sit there like sugar. They are not sugar. They are radium salts, and they are quietly ruining the future. But you are not supposed to know that yet. At first, everyone is delighted. Here is a substance that glows without charging. It does not need daylight. It does not need a lamp. It simply shines faintly blue-green like a frozen thought. And it keeps shining night after night, year after year. The first time you see it, you will think it is the perfect glow. A glow with no bedtime. Congratulations, you have found a problem that does not sleep. The glow of radium paints is not quite the radium itself shining. That is the detail people miss when they tell the story badly. Radium decays and emits radiation, often alpha particles. Alpha particles are helium nuclei, heavy and charged like tiny cannonballs. They cannot travel far in air. They are stopped by a sheet of paper, by skin, by a few centimeters of space. So they do not sound terrifying at first, but when those particles slam into a phosphor, like zinc sulfide, they excite it. They kick its electrons up, and the phosphor emits visible light. So the paint is a partnership. Radium as the restless engine, zinc sulfide as the lampshade. The radium does the decaying, the phosphor does the glowing you can see, and the result is a paint that shines constantly. Not bright like a bulb, but visible in darkness. Perfect for watch dials. Perfect for anything you want to read at night without a flame. And people wanted that very much, because flames are inconvenient in trenches, in cockpits, in factories. Flames betray you, burn you, and consume oxygen. A self-glowing dial seems like progress with good manners. It is progress with a smile and a knife behind its back. Now bring your attention to the workers, because the story is not only about chemistry. It is about bodies meeting chemistry slowly. Imagine you are one of them, seated at a long table. Your shoulders hunch forward under electric light that flickers faintly. In front of you are tiny numerals on a watch face. You hold a brush that must be very fine. The paint must be applied precisely. The paint is a suspension of radium compound and phosphor in a binder. It is thick, gritty, and it dries quickly if you do not work fast. The supervisor wants crisp lines, so you are taught a technique. Lip, dip, paint. You put the brush between your lips to make a point. You dip it in the paint. You paint the numerals. You repeat over and over. Each time, you swallow a little. Each time, you coat your mouth with invisible particles. In daylight, you look like a person doing careful craft. In darkness, you and your co-workers glow faintly. Your dresses have specks of light on them. Your hands shimmer. Your teeth may even sparkle when you laugh. It is charming in a horrifying way. The workers called it ghostly and sometimes played with it. Paint a nail, touch a cheek, leave a glowing fingerprint on a friend. It felt harmless because it was slow, and because the body does not have pain receptors for radiation. You cannot feel an alpha particle tearing through tissue if it is inside you. There is no sting, no heat, no warning, just time. This is the soft horror of self-glowing paint. It does not explode. It does not announce itself. It simply keeps doing its job, and your body pays for the convenience. Radium behaves chemically like calcium. That is the trap. Your body loves calcium. It uses it to build bones and teeth, to run nerves, to squeeze muscles. So if radium gets into your bloodstream, the body can treat it like calcium and store it. It gets deposited into bone, and then it sits there, decaying, right next to marrow, where blood cells are born, right next to sensitive tissue that was never meant to be irradiated from inside. So, the most dangerous radiation is not the kind that hits your skin. It is the kind you convince your body to hold on to. Alpha particles are not very penetrating from outside, but inside bone, they do not need to travel far to cause damage. They slam into cells, break chemical bonds, and leave chaos behind. Not instantly, over months and years, slow enough that it looks like bad luck at first. Teeth loosen, jaws ache, infections do not heal, bones become fragile, anemia creeps in as marrow fails. The details are grim, but the mechanism is simple. Ionizing radiation damages DNA. Cells try to repair it. Sometimes they succeed, sometimes they fail quietly, and sometimes they survive with the wrong repairs and become cancer. That is what makes this kind of danger so psychologically cruel. It is probabilistic. It is delayed. It does not pick one outcome and commit. It rolls dice for years. Now, the Victorians you started with did not paint with radium. This is slightly later, but it grows from the same cultural hunger for glow, the desire to carry light into darkness, the desire to cheat the night. And the industrial world loved any cheat that scaled. A phosphorescent powder must be charged. A radium dial does not. So businesses saw reliability. Governments saw utility. Consumers saw romance. And workers saw a paycheck and a craft. And no reason to fear the paint, because the people selling it did not fear it either. At least not at first. Even scientists handled radium with casual fascination. They carried samples in pockets. They stored it in drawers. They admired its glow like a pet that never slept. There were stories of radium warming itself because it releases heat as it decays. A tiny heater in a vial, a piece of matter that refuses to be inert. That is what made it feel like a miracle that could fit in your hand. But miracles are just physics you have not suffered from yet. The radium paint era produced tragedies that later forced a change. Not because society became kind, because lawsuits and bodies made denial expensive. Regulations arrived the way they often do, late, written in the ink of avoidable harm. Brush licking stopped being taught. Ventilation improved. Protective practices became normal. Eventually, radium paint was replaced by safer luminous technologies. But do not let that sound like a neat ending. Radium has a long half-life. It stays radioactive for a timescale that ignores human careers. So, contaminated objects remained contaminated. Old dial factories stayed hot in a radiological sense. Waste was buried, moved, forgotten, then rediscovered. The glow kept going, faintly, even when the fashion for it died. That is another lesson of self-glowing materials. they are not really glowing for you. They are glowing because decay is happening, and decay does not care about your interest. Now, in the spirit of being calm and factual, you can separate the fear from the mechanism. A self-glowing radium paint is dangerous mainly when particles get inside you. Outside the body, the risk depends on shielding, distance, and time. Inside the body, the risk becomes intimate. That is why the workers suffered more than the customers. The dial on a wall is mostly an external exposure, often small. The paint in your mouth is an internal exposure, persistent and brutal. It is the difference between standing near a campfire and swallowing embers. Same source, different consequences. And it also shows you a broader truth. The same physical phenomenon can be a tool or a hazard depending on how it meets flesh. Radiation can image bones in a hospital. Radiation can also shred bone marrow in a factory worker. Context is everything. And ignorance is a context too. The self-glow chapter is unsettling because it reveals how easy it is to confuse a helpful effect with a harmless cause. A glowing number is useful. So the substance that makes it glow must be useful too, people assume? That assumption is a human shortcut. Nature does not reward shortcuts. Nature waits patiently for you to touch the hot part. Now, let your attention slide back toward chemistry that does not require lawsuits to understand. Because even in a sleeping house, chemistry is working around you. Not dramatic chemistry, not explosions and colored flames, the slow, quiet chemistry of air. You are surrounded by gases that behave like a lazy ocean. They mix, they drift, they bump, they trade energy, they forget where they came from. Air is mostly nitrogen, a gas that is content to do nothing. Oxygen is the restless minority, eager to react, eager to support fires in metabolism. And then there are the tiny guests. Water vapor, always. Carbon dioxide, rising gently with every breath. Traces of other things, depending on where you live. A whisper of cleaning product. A faint thread of cooking oil. A memory of smoke trapped in fabric. In a Victorian house, the air chemistry had a personality. Coal smoke, soot, sulfur compounds, gaslight byproducts, depending on the quality of the gas. Candle wax vapor, warm and faintly sweet. Varnish and linseed oil curing on woodwork, releasing sharp organic molecules. Damp stone in basements, bringing a mineral coldness to the smell. Mold in corners, sending out earthy notes like unwanted letters. You would not call it indoor air quality then. Instead, you called it the smell of home, and you learned to stop noticing it. You are lying in bed now, but imagine you are in that older house where the air has weight. You think air is empty, like a gap between objects. Wrong. It is crowded. It is busy. It is full of collisions you never signed up for. Every breath you take is a small chemistry lecture delivered directly to wet tissue. Your nose is not smelling air itself. You are detecting stray molecules, little trespassers, that dissolve into mucus and press buttons on receptors. One molecule can be enough if it fits the receptor shape like a key. Two different molecules can smell the same if your nervous system panics and labels them quickly. And the reverse is also true, because biology enjoys being unhelpful. One molecule can smell different depending on concentration, because your receptors saturate and your brain improvises. In a Victorian house, smoke was not just an event. Smoke was an ingredient in daily life because coal and wood were the default. Coal smoke carries sulfur compounds and tiny carbon particles and trace metals that wrote in on geology. If you had gaslight, you also had combustion inside the room, even if it looked civilized. Early gaslighting often used coal gas, a mix that could contain hydrogen, methane, carbon monoxide, and other bits that do not belong in lungs. The flame was small, but it ran for hours, so the runes slowly accumulated. What the flame made: carbon dioxide from combustion, water vapor from combustion, and, if the combustion was imperfect, carbon monoxide, which is a silent liar of a molecule. Carbon monoxide looks enough like oxygen's usual partner that your hemoglobin grabs it and refuses to let go. Hemoglobin is your red blood cell's proud little claw. It is meant to hold oxygen, then release it where needed. Carbon monoxide binds far more tightly and turns that claw into a trap. Congratulations, your blood is now carrying passengers that do not pay fare. You can feel fine at first because your body is generous with emergency capacity. Then you get a headache, then dizziness, then confusion, then nothing dramatic at all, just an abrupt end. Victorians learned this in the slow way, through accidents blamed on bad air, bad luck, and weak constitutions. They did not have cheap detectors. They had canaries and instinct and sometimes a sudden quiet. Now, pull your attention away from disaster and toward the gentler chemistry. Even in a safe, modern bedroom, your air is not stable. It is stratified, layered by temperature. Warm air rises, cooler air sinks, and the whole room becomes a slow-turning aquarium. Your body is a heater, a small, constant engine turning food into warmth and pushing it into the room by convection. That is why you can feel cold even in a warm room. If the air is moving, moving air steals heat more efficiently because it strips away your warm boundary layer. In an older house, drafts did that constantly. A crack in a window frame, a gap under a door, a chimney pulling air upward like a lazy vacuum cleaner. The physics is simple. Hot air is less dense, so it rises, and it must be replaced. So outside air is pulled in at the edges, and the building breathes whether you want it to or not. That breathing carried smells: coal smoke from the street, damp earth from the foundation, oil from the workshop next door, and indoors, your own chemistry added more. Every exhale is warm, wet air loaded with carbon dioxide. It also carries trace compounds from your metabolism, tiny ketones, faint alcohols, a whisper of the internal factory you live inside. Your skin emits oils that slowly oxidize in contact with oxygen. Those reactions are not dramatic, but they are real. Oxidation is simply electrons being stolen, one polite mugging at a time. The byproducts have smell. That is why old books smell like old books. The paper and glue and ink slowly break down, releasing volatile organic compounds in small, steady amounts. The same thing happens to varnish on wood and to paint binders on walls. Linseed oil, for example, hardens by reacting with oxygen. It polymerizes, meaning small molecules link into larger networks. While that happens, it can release aldehydes and other volatile bits that drift into air. You smell them as sharpness as that fresh paint sting, In a Victorian room with newly varnished furniture, that sting could last for days. And because the ventilation was inconsistent, the sting could settle into fabric and linger. Now consider the strange intimacy of humidity. Water vapor in the air changes everything, quietly. It changes how heat feels on your skin. It changes how dust clumps. It changes how odors travel. Because many molecules hitch rides on moisture, humidity also changes static electricity. Dry air lets charge build up on surfaces because water is not there to leak it away. That is why winter air can crackle with tiny sparks. That crackle is chemistry and physics sharing a hallway. In older homes, humidity could be high from washing, cooking, and bodies, especially in winter when windows stayed shut. That made mold more likely because mold is an opportunist with a simple job description. Spores land, find moisture, find food, then build a colony. The food can be wallpaper paste, wood, dust, even old fabric. The smell is often described as earthy. It is actually microbial metabolism. Volatile compounds released as fungi digest material. You are smelling decomposition gently. Now imagine you are a single oxygen molecule in that room. You drift, you bounce, you ricochet off furniture, off walls, off a sleeping person's blanket. You are not moving with purpose. You're following statistics. Brownian motion, the ceaseless jitter caused by thermal energy. You eventually reach a nose, but you do not get detected as oxygen. You slip past olfactory drama because your chemistry is too common. Then you reach lungs, where the environment changes completely. It is warm, wet, and lined with membranes so thin they are almost an insult. In the alveoli, oxygen diffuses into blood because there is a gradient. More oxygen in air, less in blood. So it flows down the difference like water down a slope. It is not thinking, it is obeying thermodynamics. And carbon dioxide diffuses the opposite way. Your body is, at its core, a controlled combustion system that never quite finishes the burn. It takes glucose and oxygen and produces carbon dioxide, water, and usable chemical energy. The usable energy is stored in adenosine triphosphate, a molecule with 3 phosphate groups. Triphosphate, meaning 3 phosphates, meaning a spring-loaded arrangement of bonds. Break 1 phosphate off, and you release energy. That energy runs pumps, builds proteins, moves muscles, and the waste heat drifts out into your room, joining the background. This is why your bedroom never truly stops changing, even when everything seems still. Now, shift your imagination back to the Victorian interior. The walls might have wallpaper colored with intense pigments. Some were gorgeous, and some were lethal, and sometimes those were the same ones. Arsenic-based pigments, like Scheele's green and Paris green, made bright, fashionable greens. If the wallpaper got damp, fungi could metabolize arsenic compounds and produce volatile arsenic-containing gases. There is debate about how common this was, but the chemistry is plausible. Moisture, microbes, and arsenic in a room, it is not a soothing triangle, and it fit the Victorian pattern. Beauty first, consequences later, if at all, even without arsenic drama. Dust was a constant. Coal soot settles, as fine particulate matter. It darkens curtains, it coats shelves, it works its way into lungs. You do not notice it quickly because it is gradual, but it changes the chemistry of surfaces because soot absorbs compounds. Adsorption is not absorption. Adsorption means molecules stick to a surface like gossip to a bored mind. So soot becomes a sponge for odors and pollutants. It can then release them later, slowly, like a wall that remembers. That is one reason old houses have a persistent smell that cleaning cannot fully erase. They are chemically seasoned. Now, to keep things gentle, bring your focus to a smaller, calmer reaction. You are watching a glass of water on a bedside table. It looks still. It is not. Water molecules are breaking and reforming hydrogen bonds constantly. Hydrogen bonding is a weak attraction between the slightly positive hydrogen and slightly negative oxygen of neighboring molecules. It is not a true bond like the ones within the molecule. It is more like a group of strangers leaning toward each other in a crowded carriage. This constant rearrangement is why water is liquid at room temperature. It has enough cohesion to cling, but not enough to freeze into one rigid structure. That same water is also interacting with air. Oxygen and nitrogen dissolve in it a little. Carbon dioxide dissolves too and reacts with water to form carbonic acid, a weak acid, but enough to make pure water slightly acidic if it sits exposed. That is why rain is not perfectly neutral. It always carries some carbon dioxide. In Victorian cities, rain carried more. Sulfur dioxide from coal combustion reacts in the atmosphere to form sulfurous and sulfuric acids. That is acid rain, long before the term became popular. It etched stone, corroded metal, and quietly rewrote building surfaces. So when you picture a soot-blackened statue in an old photograph, you are not just seeing dirt. You are seeing atmospheric chemistry sculpting with acids and particles. Now, speaking of quiet indoor changes, think about the air near a flame. A candle is a small chemical reactor. Wax melts, wicks upward, vaporizes, then burns in oxygen. If the flame is well fed with oxygen, you get mostly carbon dioxide and water. If it is oxygen starved, you get soot, carbon monoxide, and a mess of partially oxidized organic compounds. That yellow candle flame color is partly glowing soot particles. They are hot enough to incandesce, radiating light like tiny heated stones. So a candle is not just burning gas, it is making and burning soot in the same breath. In a Victorian drawing room, candles were everywhere. So you had light and heat and air chemistry, all braided together. Now, let the scene drift into the next place your mind naturally goes. The shelf, the bottles, the Victorian love of liquids and glass, lined up like polite soldiers. You move through a hallway into a small apothecary-like corner. The air changes. Less smoke, more alcohol and herbs, more camphor, more sharpness. Your fingers brush cool glass. Each bottle holds a story and a reaction waiting to happen. Some bottles hold ethanol, the same alcohol that appears in wine and spirits. Ethanol is a solvent, which means it is good at dissolving certain compounds. It has a polar end and a non-polar end, a chemical diplomat. That makes it useful for tinctures, perfumes, varnishes, and cleaning. It also evaporates easily, so its scent blooms fast. In a quiet room, you can almost see evaporation as a kind of invisible fog, molecules leaving the liquid surface, joining the air, diffusing outward. Diffusion is slow, but it never stops. It is the same mechanism that spreads a smell from one corner to the whole room. And it is the same mechanism that spreads a pollutant. The difference is whether you like the smell. Victorians kept oils too. Turpentine, distilled from pine resin, used to thin oil paints and clean brushes. Turpentine smells sharp and forest-like, but it is also an irritant. It is made of terpenes, organic molecules that evaporate and can react in air. In sunlight, terpenes can participate in atmospheric chemistry, contributing to ozone formation. Indoors, they mostly contribute to headaches if you use too much in a small room. But they were common because painters existed, and so did people who insisted on glossy furniture. Shellac was another staple, a resin secreted by insects, dissolved in alcohol, used as a finish. It dries fast, it shines, and it smells like solvent. The finish hardens as the alcohol evaporates, leaving a resin film. So much of Victorian chemistry is just that, a liquid carrying solids. Then the liquid leaves. Then the solids stay in a new arrangement. Paint, varnish, ink, perfume, all variations on the same theme. Carrier, pigment, binder, evaporation. Now you watch a small demonstration that looks like calm magic. A drop of dye falls into water. It blooms like a slow underwater flower. That bloom is diffusion plus convection. Molecules move from high concentration to low concentration. If the water is still, diffusion dominates and the bloom is smooth and slow. If the water is warmer in one spot, convection adds swirling currents. In the Victorian mind, this kind of blooming color was proof of invisible motion. You did not need equations to feel it. You could see it in the way a drop spreads, and you could never pull it back together. That one way, spreading is entropy. Again, wearing watercolor. Now consider a more dramatic but still gentle reaction. Vinegar meets chalk. The hiss is carbon dioxide being released. Vinegar is acetic acid, a weak acid. Chalk is calcium carbonate. Acid meets carbonate, and carbon dioxide gas is freed. The chemistry is simple. The effect is satisfying. Victorians loved reactions like this, not because they were useful always, but because they performed. A fizz is a visible confession that atoms rearranged. You can do it in a kitchen, and suddenly you are doing chemistry. Now think of pigments, because pigments were the real obsession. Pigments are tiny particles that absorb some wavelengths and reflect others. Their color is what remains after absorption. Black pigments like lamp black were made by collecting soot. Soot, again, the same carbon particles from incomplete combustion. White pigments included lead white, basic lead carbonate. It covered beautifully, and it poisoned beautifully, because lead does not need much encouragement to harm. Lead interferes with enzymes, disrupts nervous systems, and accumulates. In a painter's studio, lead dust was everywhere. In a nursery painted with lead, lead chips could end up in mouths. People did not always connect the cause to the effect. Slow harm looks like misfortune. Bright pigments came from metals too. Cinnabar, mercury sulfide, made a vivid red called vermilion. Mercury compounds have their own long list of tragedies. Copper compounds made greens and blues. Ultramarine, once made from lapis lazuli, was expensive enough to be a status symbol. Later, synthetic ultramarine made the color accessible, a chemical democratization. And then there were organic pigments, dyes from plants and insects. Cochineal from crushed insects made reds. Indigo from plants made deep blues. Madder root gave another red. These dyes often needed mordants, metal salts that help fix color to fabric. Alum, iron salts, tin salts, each changing the final tone. So a color on a dress was not just fashion, it was coordination between organic molecules and metal ions. Now, because you are here for glow and weirdness, notice how these pigment stories touch luminous materials too. Many phosphors were sulfides, often zinc sulfide, sometimes with added copper or other dopants. Dopants are deliberate impurities. You add a tiny amount of another element to create energy levels that help trapping an emission. It is like putting a specific bump in the road so electrons stumble and linger. Victorians did not always use the word dopant. They used recipes. A pinch of this, a little of that. Heat until it behaves. And sometimes the recipe worked because of contamination they did not know was there. Now, step closer to the shelf of bottles again. You find acids, because every era that pretends to be scientific loves acids. Sulfuric acid, called oil of vitriol, thick and dangerous. Hydrochloric acid, often called spirit of salt. Nitric acid, aqua fortis, strong water, because naming likes drama. Acids in glass bottles are quiet until they are not. Their hazard is in contact. They burn by donating protons, disrupting molecules, tearing apart proteins and tissues. Your skin is not designed to be in a proton donation contest. Bases were there too. Ammonia, sharp and choking. Lye, sodium hydroxide, used in soap making. Bases burn by accepting protons and breaking down fats, turning skin into soap, which is not a compliment. Yet in daily life, diluted acids and bases were useful. Vinegar for cleaning, soap for washing, ammonia for shining glass. Chemistry in a house is often about moving grease from one place to another. Now, watch a Victorian perfume being made. Essential oils dissolved in alcohol. A little lavender, a little bergamot, a little musk, sometimes from animals, because ethics was not invited. Perfume works because volatile molecules evaporate and reach noses. Top notes evaporate fast. Base notes evaporate slowly. So a perfume is a time-release system, but made of smell. The chemistry is again diffusion and volatility, and the human brain's habit of attaching emotion to molecules. Now, let your mind return to glow paints, because they lived on those shelves too. A jar of luminous powder, a bottle of binder, a small dish for mixing. You add powder to varnish. Stir until suspended. Suspension means particles floating in liquid, not dissolved, just carried. If you let it sit, it settles, because gravity never forgets. Stokes's law describes settling speed for small spheres, but you do not need the equation. You can see it. A cloudy jar becomes layered, clearer at top, thicker at bottom. So you shake it, and the particles rise again, briefly. That motion, that temporary uniformity, is the everyday labor of chemistry. Keep it mixed long enough to apply, then let it settle permanently as a film on wood or metal. Now, a note about glass, because all these bottles depend on glass behaving. Glass is not a crystal. It is an amorphous solid, a liquid-like structure frozen in place, mostly silica, with additives like sodium and calcium to lower melting temperature and adjust properties. Old glass can be slightly reactive. Some types leach alkali over time. That can create a hazy surface, a kind of disease called glass crizzling in extreme cases. So even the container participates. Slowly, nothing in chemistry is truly inert, just slow enough for you to stop caring. Victorians also loved colored glass, uranium glass, for example, tinted yellow-green by small amounts of uranium. It fluoresces under ultraviolet light, glowing green. In daylight, it looks like a cheerful novelty. In a dark room with a suitable lamp, it becomes eerie. The uranium concentration is usually low, and the radiation risk is typically small compared to radium paint horrors. But it is still a reminder. People have always been willing to put strange atoms in decorative objects if the result looks nice. Now, drift into one more quiet reaction you could almost hear if you were small enough. Rust. Iron reacting with oxygen and water to form hydrated iron oxides. Rust is an electrochemical process. It involves electrons moving from iron to oxygen, facilitated by water. Salt speeds it up by making the water more conductive, so coastal air with sea salt aerosols makes iron decay faster. In Victorian cities, air pollution could also accelerate corrosion. Sulfur compounds could form acids on wet surfaces, increasing reaction rates. So, metal railings and bridges were always in a slow war with air. Paint was partly armor. Oil paint forms a barrier to oxygen and water. But if the barrier cracks, rust begins at the crack and spreads underneath, lifting the paint, so you repaint. Again and again, a cycle of maintenance driven by oxygen's relentless social life. Now, if you lift your gaze from shelves and walls, the mind naturally wants to go upward. The ceiling, the window, the night sky. The glass is cool under your fingertips, and it does not care what century you are in. The window is a thin membrane holding back a whole vacuum of weather. Beyond it, the darkness looks like a single thing, but it is layered, like paint. You think the night sky is black because it is empty. Wrong. It is black because most of it refuses to interact with you at all. What you call darkness is usually just light that missed you. Moonlight, for example, is not a gentle lamp hung in space. It is sunlight that took a detour, bounced off powdered rock, and arrived tired. You are seeing the sun indirectly, like hearing gossip through three neighbors and a closed door. The moon's surface is covered in regolith, a fine, sharp dust made by impacts, not soft beach sand, more like powdered glass and broken stone. That dust scatters sunlight in a complicated way, and some of it reaches your window. The light feels silver, but that is your brain dressing it up. Spectrally, it is mostly sunlight with its brightness turned down and its angles changed. And because your night vision leans toward bluish-green sensitivity, The whole scene shifts emotionally. That is not poetry. That is rods again, quietly hijacking your aesthetics. Moonlight is borrowed brightness, and it comes with a schedule. Half the month, the moon offers you more. Half the month, it offers you almost nothing. Even when it is full, the brightness is still faint compared to daytime. You do not notice how faint until you try to read fine print by it. Your eyes want to, and they cannot quite commit. Now turn your attention to the stars, because they are the original glow-in-the-dark paint. They look steady and small and polite, but they are violent furnaces, and you are seeing their exhaust. Starlight is not light that belongs to tonight. It is light that left long ago and finally found your face. Some photons crossed space for years, some for thousands of years, some for longer than your species has had language. They arrive without context, and your brain assigns them a twinkle. That twinkle is not the star-changing mood. It is Earth's atmosphere bending and wobbling the light, like heat shimmer over asphalt. Air has different densities in different places, especially when it is turbulent. Different density means different refractive index, meaning light bends differently moment to moment. So, the star seems to flicker, even though the star is doing its own separate drama, far away. You could call it a cosmic light show, or you could call it your atmosphere being messy in public again. And while you are watching Starlight, you are also watching time, not philosophically, but literally. A star that looks bright might already be dead, in the strict sense. Its light is a delayed letter, delivered long after the sender stopped writing. You stand at your window, and you realize you live inside a museum of old photons. You think you are seeing the sky as it is. Wrong. You are seeing the sky as it was. Now, since you came here for glow, notice how much of the night glow is not from space at all. Some of it is from the air above your head. The atmosphere can glow faintly, even on nights without aurora. This is called air glow, and it is the planet's own quiet fluorescence. Sunlight during the day breaks molecules apart and energizes atoms. At night, some of that energy relaxes back out as faint light. Oxygen can emit green and red light in the upper atmosphere. Hydroxyl radicals can emit in the infrared a soft warmth your eyes cannot see. It is not bright enough to notice in a city, but under dark skies, it gives the night a subtle texture, a background sheen, a reminder that even darkness has emissions. The Victorians loved any glow that felt like the sky admitting secrets. Auroras were the most dramatic example, and also the most misunderstood for a while. They would watch curtains of green and red moving across the horizon. They would write about celestial battles, or electric ether, or spiritual signs. The real mechanism is less theatrical and more satisfying. Charged particles from the sun, carried by the solar wind, get guided by Earth's magnetic field. They spiral down toward the poles and collide with atmospheric gases. Those collisions excite oxygen and nitrogen. When those gases relax, they emit photons and you see ribbons of light. It is basically the planet being hit by invisible hail and answering with color. You are safe from most of that because of the magnetic field and the atmosphere. Congratulations! You are living under a shield you rarely thank. Now pivot gently down from the sky to the ocean, because Earth has its own night glows too. Sometimes the sea glows and it looks like spilled starlight. Bioluminescent organisms, often dinoflagellates, can emit blue light when disturbed. That glow is not borrowed from the sun the way phosphorescent paint is. It is chemical energy converted into light inside cells. Luciferin and luciferase are the famous pair, a molecule and an enzyme that react to make photons. The reaction is efficient compared to a candle because it wastes less energy as heat. It is what people call cold light, though it is not actually cold, just not burning hot. And it is used for a reason that is not sentimental. Communication, camouflage, luring, startling predators, confusing prey. Nature does not make decorative lighting. It makes survival tools that happen to be pretty. So when Victorians marveled at luminous waves, they were watching chemistry with a job. Speaking of jobs, return again to the moon, because it teaches another lesson about borrowed brightness. The moon is bright mainly because it reflects sunlight, but it is actually a dark rock. Its reflectivity is low, closer to worn asphalt than clean snow. It looks bright because the night around it is darker, and your eyes adapt. Context makes brightness feel larger. That is also why glow paint looks impressive in a dark room. It is rarely strong light. It is light surrounded by less light. Now, bring your focus back inside, because the window is only a thin distraction. Somewhere in the house, a small modern glow is waiting for you. A night light, a luminous sticker, a watch face that does not require radioactive salts and tragedy. Modern glow pigments are designed to be stable, predictable, and boring in the best way. Instead of zinc sulfide as the main long glow material, many modern long afterglow pigments are based on strontium aluminate. Strontium aluminate is a ceramic-like compound, and when doped with rare earth elements, it can store and release energy efficiently. Doped means deliberately contaminated, because again, perfection is bad for glow. Europium is a common dopant, and dysprosium often helps extend the afterglow by creating deeper traps. You do not need to memorize the names. Just notice the pattern. A host crystal plus carefully chosen flaws equals a controlled delay in light emission. This is the Victorian workshop upgraded into industrial consistency. Same idea, better discipline. Strontium aluminate pigments can glow longer and brighter than the older sulfide-based ones, and they degrade less quickly. They are also less likely to come with a bonus hazard that sues you. The pigment grains are often coated to protect against moisture, because water can still interfere, and the binders are chosen to stay clear, so the glow is not filtered into sadness over time. A modern night light can be plastic, ceramic, or an electronic device with a light-emitting diode. A light-emitting diode is a semiconductor that emits photons when electrons recombine across an energy gap. That gap decides the color. The same general confession you saw in phosphors. But unlike a glow pigment that slowly leaks, a diode glows as long as current flows. And as long as your power grid keeps its promises. That is another kind of borrowed light, just borrowed from generators far away. Still, for the specifically glow-in-the-dark materials, the charging is gentle. Room light charges them. A desk lamp charges them. Even a cloudy day can charge them, slowly. Then they fade slowly over hours, not minutes. The curve is still there, bright at first, then a long tail of dim persistence. It feels like the object is breathing out a memory of light. And in a safe bedroom, that is what you want. A glow small enough not to demand attention, but present enough to reduce uncertainty. Because the human mind hates obstacles in the dark. It hates sharp corners and unknown distances. A faint marker on a hallway edge is not magic. It is a compromise between your ancient nervous system and your modern furniture choices. Now, it is worth being annoyingly precise about what modern glow pigments are not doing. They are not nuclear. They are not radioactive in normal consumer products. They are still doing the same basic phosphorescence trick, using electron traps. Energy in, energy stored in metastable states, energy out as photons. Metastable means stable enough to linger, but not stable enough to last forever. Like a badly stacked pile of books that has not fallen yet. Eventually, thermal motion will nudge the trapped electrons out. Eventually, the afterglow ends. That ending is not a defect. It is the guarantee that the material is not secretly fueled by something worse. Now think about the word safe, because it is always relative. Safe does not mean nothing can happen. Safe means the risks are understood, minimized, and made boring. Modern pigments still come as powders. Powders can still be inhaled, and you still do not want that. The difference is that now you get labels and standards and hazard sheets, not because humanity became wise, because it became litigious and occasionally ashamed, and because the chemistry itself improved. The glow is now engineered with care instead of guessed at with recipes and superstition. Speaking of engineering, notice the strangely emotional design choices in night lighting. Blue light feels bright at low levels because your rods like it, but blue light can also affect circadian rhythms more strongly because of melanopsin-containing cells in the retina. Those cells influence your internal clock, nudging your brain about day and night. So, modern night lights often aim for warm amber colors, not because amber is romantic, but because it disturbs sleep less. That is chemistry and biology negotiating your bedtime. Some night lights use red light for the same reason. Your rods are less sensitive to red, so it feels dimmer. And your sleep signaling system is less bothered by it. It is the opposite of Victorian glow paint choices, which favored green for visibility. Same eyes, different goals. Victorians wanted to see the clock without lighting a candle. You want to avoid waking the brain too much while you do it. Your priorities have shifted because now light is cheap and sleep is expensive. Now, while you are thinking about cheap light, remember that modern lighting is usually not a smooth, continuous glow. Many light-emitting diodes flicker at high frequency because of how they are powered. You may not consciously see it, but cameras do. And sometimes your nervous system senses it as fatigue. The room seems steady, but it is pulsing slightly, like an electronic heartbeat. Incandescent bulbs glowed with a hot filament, with less perceptible flicker. They were inefficient heaters that happened to emit light. Light-emitting diodes are efficient, but they come with electronics that sometimes chop current into pulses. Even your calm, modern room has hidden rhythms. Now return to the physical glow pigments again, because they have a charming limitation. They need charging, and charging is basically just filling traps. If the traps are already full, more light does not help much. This is why leaving glow objects under a lamp all day does not create infinite brightness. There is a saturation point. The traps are occupied, and the material cannot hold more in that way. So brightness has a ceiling, and the glow time has a rough maximum, depending on trap depth distribution. Trap depth is the energy barrier keeping electrons stuck. Shallow traps release quickly. Deep traps release slowly. A good long afterglow material has a mix, so it is bright early and persistent late. This is less like a battery and more like a crowd leaving a theater. Some people rush out immediately. Some linger in the aisles. Some get stuck behind a slow group and take forever. The glow is the sound of them leaving. Now consider the role of temperature again, because your bedroom is not always the same temperature. A colder room tends to slow the release of trapped electrons, so a glow object might last longer but appear dimmer at any given moment. A warmer room can make it brighter early, but shorter lived. It is the same idea as before. Thermal energy as a key. You can even feel this if you hold a glow object in your hand. Your palm warms it, and the glow may surge slightly, then fade faster. It is subtle, but it is real. Your body is always interfering in experiments just by being warm. Now, since you are in a modern house, notice the quiet chemistry of the materials around that glow. Plastics, for example, are polymers, long chains made from repeating units. They can yellow over time, crack, and release small amounts of additives, plasticizers, stabilizers, flame retardants, all the quiet guests that make consumer goods behave. Some plastics absorb smells and release them later, adsorption again, the surface gossip effect, but now in polymer matrices. So your glow sticker is not just pigment, it is pigment embedded in polymer, living in air, interacting with humidity, oils from fingers, and ultraviolet light from the sun. Ultraviolet can break polymer chains, causing fading and brittleness. That is photodegradation, and it is a slow sunburn for objects. This is why things left in sunny windows get tired and brittle. The sun charges glow pigments, yes, but it also ages their hosts. Everything is trade-offs. Now shift to the simple switch glow, the one you control, the one that does not rely on stored energy at all. A bedside lamp turns on, and photons appear instantly. It feels like creation, but it is just a circuit closing. Electrons move through a wire pushed by an electric field. In a filament bulb, they heat a thin wire until it glows. In a diode, they recombine in a semiconductor and emit light directly. In both cases, you are paying for a controlled loss of energy. That is what lighting is, the deliberate production of entropy that happens to be useful. It is a civilized fire, but still a fire in concept. Now, because you started in Victorian glow paints, it is worth remembering how much effort once went into making light at all. A candle is stored chemical energy in wax. An oil lamp is stored chemical energy in oil. A gas light is stored chemical energy in gas. All are small, controlled combustions. Modern light is usually stored chemical energy too, just burned far away in power plants, or captured by solar panels, or released by batteries. The difference is distance. The mess is outsourced. Your room stays clean, and the chemistry happens elsewhere. That cleanliness makes modern light feel innocent. It is not. It is simply someone else's exhaust. But for bedtime, You do not need that whole infrastructure story. You only need the intimate part. A small, steady light that makes the room legible. Now, think about why small lights feel comforting. Your brain is constantly building a map of your surroundings. In darkness, the map has missing data. Missing data forces guesswork. Guesswork invites fear, or at least mild irritation. A night light reduces guesswork. It gives your visual system anchor points, edges, shapes, the location of the door, the outline of furniture. It turns the unknown into the mundane. And this is why glow-in-the-dark paint was never just a novelty. It was always partly about control. Control over night, over navigation, over uncertainty. Victorian glow marks on stairs were safety devices before they were toys. Modern glow strips on exit signs and pathways serve the same purpose. In some buildings, photoluminescent exit path markings are used because they work even if power fails. Charge them with normal lighting, and they guide people when the electronics go dark. It is the same old trick, used responsibly. Borrowed light, stored briefly, released when needed. The comfort is not the glow itself. The comfort is what it promises, a path. Now, since you are still looking at the window, let your mind take one more gentle detour upward. Not to the stars this time, but to the thin shell of atmosphere that makes any of this survivable. The air above you is not just a mix of gases. It is also a filter. It blocks much of the sun's ultraviolet, especially the more energetic kinds that shred DNA quickly. Ozone in the stratosphere absorbs ultraviolet strongly. Without it, life on land would be far more constrained, and your skin would be a different kind of organ entirely. So the same sunlight that charges glow pigments also carries wavelengths that would sterilize surfaces if unfiltered. The world is balanced on selective absorption. Absorption is not always bad. Sometimes absorption is the reason you are allowed to exist. Now bring your attention back down again to the controlled glow of modern objects. There is another older glow technology that sits between radium tragedy and modern photoluminescent ceramics: tritium. Tritium is a radioactive form of hydrogen, and it emits beta particles, which are fast electrons. In self-luminous exit signs and watch markers, tritium gas can be sealed inside tiny glass tubes coated with a phosphor. The beta particles excite the phosphor, and the phosphor emits light. It is similar in concept to radium paint, but with different radiation type and safer containment. Safer does not mean harmless. It means managed. The glow is sealed, and the quantity is controlled. The tubes are designed not to be opened by casual use. You do not lick them with a brush, which helps. And tritium has a shorter half-life than radium, about 12 years, so it fades over a human timescale. It does not persist for geological disrespect. Still, it is a reminder that self-glow is always a negotiation with nuclear physics. If you want a light that never needs charging, you are either running electricity or you are tapping a decay process. Those are the options. Everything else is borrowed light on a timer. Now, because this is a cozy story and not a safety briefing, return to the simplest modern glow again. A glow star stuck to a ceiling.